Hello and welcome back to the channel. In this video, we'll talk about self-attention, which is the foundation for understanding the transformers architecture, and then for the large language models. In this video, we'll just talk about self-attention. Let's first address the long sentence problem. Why RNNs and LSTMs fail? Let's start with one long sentence. The animal that crossed a busy road after seeing many fast-moving cars was extremely tired. As humans, we instantly notice something. Road and cars are closely related. Roads have cars, cars move on roads. But early neural networks struggled to capture this. Why RNNs failed? RNNs read text one word at a time. By the time the model reaches cars, the word road is far back. The association weakens, context basically fades away. Then why did LSTMs didn't fully fix it? LSTM introduced memory gates. Now, if you want to understand LSTMs, comment in the box, and I will try and make a video on LSTMs and its memory gates. But for now, let's just understand that LSTMs introduced memory gates. They helped, but the sentence is still processed sequentially. Long-range association like road, cars remain difficult. The limitation wasn't memory, it was basically sequential thinking. Now, what was basically the breakthrough idea? The breakthrough idea came in 2017. The paper was Attention is All You Need. That's what we are talking about here. We'll just talk about the self-attention in this video and the transformers architecture in the next video. The idea was that what if words didn't rely on memory chains? What if cars could directly look at road? That idea led to self-attention. The core idea of self-attention is self-attention allows each word to ask which other words are most relevant to me. For the word cars, the answer is clearly road. So let's understand this in 6 steps, right? We will try and break it down as much as possible. The first is words to vectors. First, every word becomes a vector, a list of numbers capturing meaning. Words like road and cars end up with similar vectors because they appear in a similar context. Now let's look at basically a similarity mapping to understand this. I have already plotted this. Alright. So here, let's zoom in to understand this. You can clearly notice here that the word road, you can see here, is very much in a high relation to cars. You can see here, right? Each word and each word similarity has been measured here, kind of a similarity matrix here. I will attach the notebook also with the video, but let's first understand it. Like animal and tired are very far, like it's 0.769. Obviously the and the are the same word, so it will have a high similarity score here. Let's understand a few more words like road and cars. You can notice here is a very nice score here, 0.92, right? Similarly, like crossed and cars are having a good score, 0.809. Let's see fast moving and cars. You have a good score here, 0.813, which basically said the fast moving cars, right? Why they are having a high score? Because while training these vectors, right, they were in basically in the same window extraction length, right? The way it was trained on the embedding, the way embedding was trained on the data. We can talk about it in the next video. If you want to know how embeddings are trained, just comment it. I will make a video on top of it. But for now, let's understand this, right? That okay, so another we can see is fast moving and road. Like let's see fast moving and road, they also have a kind of a good score, but fast moving and busy are also having a good score here. This basically shows the relation between different types of words that you see here and the words that you see here. Like kind of a high score denotes a very good connection, right? So our word road and cars are having a high similarity score. That's the point you need to know right now. Okay, let's now understand the second step, query, key and value. What are those? If query, let's understand this in query, key, value. Query, what am I looking for? Key means what do I represent? Value, my information, right? And this is what is the core basic understanding of the self-attention. Let's now look at the self-attention formula that you see here. This single equation explains how self-attention works. Let's apply it to our sentence, right? The QKT that you see here is the similarity scores. The query of cars is compared with the key of all words, right? Because road and cars are semantically related, you can see here, right? The vectors align well. This produces a high similarity score. Higher dot product is equal to stronger association. Please remember this. If you are having any kind of misconception, please comment. I will try and make you understand. Now let's understand what is DK and why scale, right? Here DK is the dimension of the query and key vectors, the number of values basically inside it, basically we are saying the dimension of the vector. Larger vectors means larger dot products, so dividing by DK keeps attention scores stable. In one line, if I want to make it understand, scaling keeps attention balanced and comparable. Okay. The fifth step is understanding softmax attention weight. Softmax basically converts similarity scores into probabilities. For now, understand that softmax converts similarity scores into probabilities. I will make a separate video on it, like a small video which explains like how softmax works. Now here the model decides that high attention lead to road, lower attention to unrelated words. Attention becomes focused and meaningful here, right? At the last step, the step 6 is weighted sum of values, right? These attention weights are now applied to values. The output vector for cars. Now that includes strong information from road. This is how the model understands. Cars belong on roads. Let's now look at the self-attention heat map. Now you can see here the self-attention heat map here, right? And let's see it that our road, right, and here cars. Understand that the basically as we move forward, these are the attention weights which get higher and higher, right? If you see here cars, which is here, and road, which are very light in color, which basically means, which is very different to other colors here, right? Which basically means that the attention is basically focused right now. The algorithm is trying to focus right now on these two words. There are other words also which are being focused on. You can see here busy and tired, right? If you are busy, you are tired, like there's a semantically context, right? There's a semantically connection between busy and tired also, right? But for now, let's focus on this part here, that road and cars have a higher kind of a attention weight here, which you can see here. This attention map is basically for each of the words against each of the words that you see here. This is the query word and this is the attended word that you see here. Okay, so now that you have seen the self-attention heat map, let's understand that why this beats RNN. In RNN, there is a memory chain. Here there is no memory chain, no distance penalty. Even if road and cars were far apart, self-attention connects them directly. Now, why it's called self-attention? Query, key and value all come from the same sentence. The sentence is attending to itself, hence it is called self-attention. Okay, so self-attention lets models discover like association, not just sequence, roads and cars, cause and effects, meaning and context. This was all for in this video. I gave a brief outline of what is self-attention. In the next video, we will stack self-attention with the feed-forward layers and positional encoding and build the whole transformers architecture and understand it in deep. If you like this video, please like and subscribe. Thank you for watching.